So this is a video explanation of problem 1 on the quiz that you took on Monday of week of 2-3-14. And I'm just going to go over it. I've kind of written out the solution ahead of time. This is a little different than the usual videos where usually I'm writing as I do it. As you can see, I can still move my pen around, but I'm sitting at home while I make this video. So I wrote everything out in pencil first, and then I just figured I would explain over what I wrote out in pencil. So problem 1 was pretty quick, and most of us understood it, but there's some key concepts in here that I can still kind of teach and explain, and hopefully I can do this in less than 5 minutes. So the question says, a 1,200 kilogram car traveling at 20 meters per second is brought to rest in 2 different ways. First by slamming on the brakes. Maybe I'll go to this kind of thing. So first by slamming on the brakes, and second by gently applying the brakes. Okay, and the reason I picked these, so that you just know how I'm thinking as I make these quizzes, is because you can tell then that this is going to have a big force applied and this is a small force applied. That's at least what I'm thinking as I'm explaining it. And I'm thinking in my head, oh yeah, well you guys would, in your experience, know that if you slam on the brakes, you know, the car stops suddenly, and if you apply them gently, there's a totally different kind of stopping that goes on. Okay, so the first part was which situation will have a larger force applied to the car? Well, clearly, part A says larger force when you slam on the brakes. And what I'm thinking in my head, if we want a physics answer for that, is this section, that net force is equal to ma. I know that I have a much larger acceleration then, so I also have to have a larger net force then. That force is probably friction, but either way, you just know there's got to be a bigger force to cause a bigger acceleration. Okay, the second part then gets into the impulse momentum side of this. In which situation will the car have a greater impulse? And in my answer, I said, well, those are actually going to be the same. And so this question is really getting at, do you know the difference between force and impulse? Impulse, I'm just going to use this part down here, is equal to, we use the symbol J, and it's equal to force applied times time applied for if that force is constant. And if not, well then we'll get into what it is in the next problem that we answer a question about. But for now, we'll just think of it as force times time. Well, impulse is also equal to the change in momentum of an object. So in this case, both cars have the same mass, 1,200 kilograms. Okay, both cars are starting off at traveling at 20 meters per second, and both cars end up traveling at 0 because they're brought to rest. So they're both going to change their speeds from 20 to 0, so the same change in velocity, same mass. That means they have the same change in momentum, or same change in the amount of motion, because momentum is mass times change in velocity. So in that case then, they have the same change in momentum, and since they have the same change in momentum, by the impulse momentum theorem, they also have the same impulse. Okay, which kind of answers then part C. Part C, which car experiences the greater change in momentum? Well, we actually used that to answer part B. And so this was just checking to make sure that you knew impulse and change in momentum were the same kind of thing. They both experience the same exact change in momentum. The thing you need to pay attention to is that they, again, with an impulse, you can receive an impulse in very different ways. For the first car, okay, notice how I try to draw these J's the same size. In the first situation, the car, when you slam on the brakes, gets a really big force, so a really large force, for a very short amount of time. Notice how I drew that time really small. In the second case, I have a much smaller amount of force, but it's for a much bigger amount of time. I'm trying to physically represent this, smaller force, bigger time. So you can receive the same impulse. You can have the same change in momentum, but have it happen in lots of different ways. You could push with a big force for a short time, or a small force for a big time. One of the things we kept trying to talk about in this class was how seatbelts make use of this idea. Seatbelts make it so that you apply a smaller force for a longer period of time as you're slowing to a stop, and that way this force is not enough to break bones, whereas when you don't wear a seatbelt, you have a big force for a short time, and that is a very large force that can break bones, and so that's not good. Alright, that's video 1.